Hello. In this mini pre-lecture video, we're going to go over everything we're going to learn about in Lecture 8, very briefly. We're going to look at what's called the integrated rate law, which is used to determine the concentration of a reactant at any given time during a reaction. We're going to look at the relationship between the rate constant and the half-life. We are going to look at plotting the data where we take our reaction concentration versus time, and from that plotted data we're able to determine the order of our reaction. And lastly, we're going to look at our activation energy, the Arrhenius equation, rate, and temperature all together. Okay, so we have our integrated rate laws. First thing we want to talk about, and our integrated rate laws are going to be a combination of the general rate law and the relative rate law. And it is used to determine concentration of a reactant at any given point during a reaction. And we're going to call that reactant A at any point in time, which is going to be T. Okay. With these, they're going to be based on the order of the reaction. And we're always going to be looking at a reaction where we only have one reactant affecting our reaction rate, or our integrated rate law gets a little too messy. So we're looking at A going to B, where it can be either 0th order, where A concentration change doesn't affect rate, we look at 1st order, where A doubling causes a doubling of rate, and we will look at 2nd order. We are 2nd order reaction overall and 2nd order with respects to A, where A doubling causes a quadrupling of the rate. We will not look at 1st order with respects to 2 reactants with our integrated rate law. So we're going to look at the general rate law versus the integrated rate law. So if we have a 0th order process, our rate law is rate is equal to K, right? So we have no dependence on A concentration here. And when we take that and we combine it with our relative rate law, then we integrate over that, we get our integrated rate law, which is A at time t is equal to negative kt plus A naught, which this form of the integrated rate law shows as a y equals mx plus b. So we'll look back at that in just a minute. When we look at plotting our concentration versus time. Okay, if we have a 1st order process, our rate is equal to K times by A, and our integrated rate law is ln AT is equal to negative kt plus ln a naught. Okay, and again we have a y equals mx plus b arrangement. Lastly, we're going to look at second order, where our rate is equal to k a squared, and our integrated rate law is 1 over at. So a at time t is equal to our rate constant k times by time t plus 1 over a naught, our initial concentration. So k is our rate constant, a naught is the initial, a concentration, at is a concentration at time t, and then t is time. Generally in seconds, but we need our k and our t to be in the same time unit. So if k happens to be given in minutes, we need our time to also be in minutes. Okay, we can plot our integrated rate law. So when we plot these, we can actually tell what type of what type of order we have for our reaction by what gives us a linear plot. So if we get a linear plot when we plot a t versus time, we have a 0th order process. Okay, so what that would look like, concentration of A, T versus time. Okay, and it will look like this, where our y-intercept is our initial A concentration, and our slope is the negative of our rate constant. If we get, so if we plot A at time t versus time and it is not linear, the next thing we're going to do is plot ln at versus time. So if we get a linear plot, when we plot ln of at versus time, we have a first order process. And here it would look like this, ln a at time t versus time. We have a linear plot where our y-intercept is ln a naught, and our slope is negative k. And I'm just going to real quick write out our integrated rate laws for these, so you can see this y equals mx plus b. Here we have ln of a t is equal to negative kt plus ln a naught. And then if we've plotted both AT versus time and ln AT versus time when we still don't get a linear plot, then we probably have a second order process. So if we get a linear plot when we plot 1 over AT versus time. We have a second order process. And that will look like this. 1 over A at time t versus time. Here we're going to look like this, where 1 over A at time 0. So we have our 1 over A at time 0 is our y-intercept, and our slope is equal to k. And we can see this when we look at our integrated rate law for a second order process. Okay. The next thing we want to relate is our half-life and rate constant. So a half-life is the amount of time it takes to consume half of our reactant. Okay, so basically how long it takes for half of the reactant to be converted into product. Okay. So our half-life itself is related to our rate constant because they both basically tell us the speed of the reaction. The smaller our half-life, or the greater our K value, the faster our reaction is, or the faster our rate is. So again, it is based, our half-life is based on reaction order. So we have different half-life equations based on if it's 0th order, 1st order, or 2nd order. So for our 0th order, our half-life, T1/2, which is half-life, is equal to our initial A concentration divided by 2 times by our rate constant K. If we have a 1st order, our half-life equation, T1/2, is equal to 0.693 divided by K. The math for these are done on the PowerPoint if you want to look at them. And then our second order process, T1/2, is equal to 1 over our rate constant K times by our initial concentration A naught. Okay, so a nice easy way to relate the two. If we have a second order process where we have 1st order and 2 reactants, I told you we're not really going to go over that, and that's because the math there for the integrated rate law is very, very complicated. However, we can do what's called a pseudo 1st order. That's where we basically make it so one of our reactants concentrations are not changing while the other one is, so we can just look at one substance. So we're taking a second order process where we are 1st order in 2 reactants, and we basically make it so that the concentration of one of the reactants doesn't change. I'm going to do this by making the reactant concentration very, very high. Okay. So it effectively doesn't change. So instead we're going to look at the reactant, or the rate in terms of one substance. So even though initially we have rate is equal to Ka times by B, we actually take and we look at only one substance. So we get an effective K. So this is our K effective. So we make this concentration really big, so we can look at just this. And then we're only really looking at the change in A concentration. And then once we determine what our K is, here we can then put that into our effective rate concentration is equal to our actual K times by our B concentration. And then that will go back in to get our rate is equal to K AB. We will not be doing this in class. We'll only really be looking at this in lab, but I wanted to show you what that looks like. Okay, the last thing I want to talk about in this video is our Arrhenius equation. And this is where we're going to relate temperature, reaction rate, and our rate constant. So we have our normal form of our Arrhenius equation, where our rate constant is equal to our collision frequency factor times by e to the negative EA over RT. So K is our rate constant, A is our collision frequency factor, EA is our activation energy, R is our gas constant, and T is our temperature. This is going to be in Kelvin. Our gas constant is going to be 8.314 joules over a mole times by Kelvin. Our activation energy is going to be joules per mole. And then our rate constant unit doesn't matter. Our collision frequency factor doesn't have a unit, so just make sure that your activation energy is in joules per mole and that your gas constant is 8.314 joules per mole Kelvin. We almost never use this one. It's our least used form of this. We almost always use either the graphical form, so our y equals mx plus b form, which is going to be ln k equals negative EA over R 1 over T plus ln of A. So this is our y, our m, our x, and our B. Remembering that this is our collision frequency factor. So if we plot ln of k versus 1 over t, we get a linear relationship and we can solve for our activation energy. So again, this would be something you generally do in lab, although I would expect you to be able to, from a graph of ln of k versus 1 over t, I would expect you to be able to get information out of here, like this is ln of A, and then our slope is equal to negative EA over R. Okay, so that stuff, you should be able to look at the plot of ln k versus 1 over t and get that information. What we almost always use is what's called the 2-point form. of the Arrhenius equation. Where we take ln K2 over K1, so our rate constants is equal to negative EA over R, 1 over T2 minus 1 over T1. Our 2-point form, we can take rate constant at different temperatures and figure out our activation energy, or we can use it as a predictive tool to figure out what a rate constant would be if we have our activation energy and 2 different temperatures. Okay, so this is going to be the most common form you guys will use in this class. That's everything for this brief pre-lecture video. Bye, y'all.